Hello everyone, my name is Tony Jace and this is another physics class. The topic before us is heat, and we shall be looking at the difference between heat and temperature, for instance, because most times students misconstrue the two different concepts. So let's start off with heat. What is heat? Heat is a form of energy. You probably know that there are different forms of energy. Now, energy could take the form of mechanical energy, could take the form of chemical energy, it could take the form of heat, as we are discussing right now. So it comes in different forms. And now, why is it often misconstrued with temperature? Now, temperature is about the degree of hotness or coldness of a body. For instance, if you take something out of the refrigerator, if the refrigerator has been working for a while, you know that thing is bound to have a low temperature. It's bound to be cold. Now, when you touch that substance, maybe a bottle of drink or whatever it is you've taken from the refrigerator, what you don't say is, oh, it has no heat. What you rather say is that the temperature is low. Or if you've taken something out of the oven, because it's bound to be hot if the oven has been working. Now, you don't get to say, oh, the heat level is high, so to say. But you would rather say the temperature is high, because what you are getting when you feel the body is that you are getting a high temperature. The degree of hotness or coldness is all about temperature. But heat itself is a form of energy. Now, we could say that when the body is hot, when the body has a high temperature, for instance, if you place it in contact with a body that is not as hot, say you take a hot spoon and dip it into cold water, you find that heat will flow from the hot spoon into the cold water. And it's a matter of time, the cold water will have an increased temperature while the spoon will cool. So the temperature of the spoon drops while the temperature of the spoon rises. That's because heat just flowed from the spoon into the water. So temperature could also be said to be the property of a body that decides which way heat will flow. The property of a body that decides which way it will flow. So if the body was the hot type and you place it close to a cold body, then of course heat will flow from the hot body to the cold. That's just simply it. So heat exactly is just about that form of energy, and not about the coldness or the hotness of a body per se. Now, basically, when we look at heat there, we can say heat could be measured by a substance, a particular body we call calorimeter, while temperature is usually measured by thermometer. Of course, we have different types of thermometers. So going back to the concept of heat, let's dwell a little more on heat. So we talk about heat and we say, for instance, it is measured, like I said a while ago, with a calorimeter, and then it is also said to be the total form of the sum total of the energy possessed by a body, like the total internal energy possessed by a body. Let me throw a little more light on that. Now, we could say that our food, for instance, has a measure of energy in it. That is why some food that will say, oh, this food is deemed to have high energy, it's a high energy giving food, like it has high calories. All right, it's all because, of course, it has more. If you burn such a food, for instance, it's going to give up more heat, so it has more internal energy store in it. Whereas other food, like other food, have lower energy store in them. When you burn such, the heat energy that it will emit will not be as high as the one that is of a generally high energy content. So the calorie, which is the amount of energy level in a food, is usually a measure of how much heat store that food has. So, for instance, we take a measure of food, maybe 1 kilogram of that food, and burn it completely and see how much heat it will emit. We use this amount of heat to raise water. For instance, 1 kilogram of water, we raise the temperature. See how much energy, see how much temperature can be raised from there. We can use that to decide the energy store in that food. So one of the things that we apply heat to, is in deciding how much energy store a food has. Of course, there are many more things we could apply it to. Let's see, effects of heat, for instance, can bring about change of state of a body. Now, if I take out a block of ice from a refrigerator and leave it at room temperature for a while, maybe leave it on a dining table, after a while, what happens to the block of ice? it will melt and change state from solid to liquid. So what just brought about that change? It absorbed heat from the room. So it absorbed it from the surrounding, and that heat was used to change the state. In fact, we call that kind of heat latent heat. So it's a heat that you do not even get to measure physically with a temperature, with a thermometer. Now, if you dip a thermometer into ice that is about to melt, the thermometer will not indicate any change of temperature. It's just that all the heat that is being absorbed by that block of ice is hidden. We call it latent heat. So one of the very important effects of temperature, of heat rather, is that it causes a change of state. What else could heat bring about? Of course, apart from change of state, we can also use heat to, cook our food. Of course, you know that. Heat can do a whole lot more, like raise the temperature of a body, as we already said. And you can warm up water, take its temperature from a low value to a high value, and a whole lot more. So that's basically that about heat and then the effects. So the uses are numerous, one of which we said is like warming the food, and they're doing a whole lot. Like you can even use it to ignite an engine. To ignite the engine, to get the engine of a car, for instance, to start, the spark plug must fire up the fuel and let the fuel, turn into fumes, into vapor. That could be used to start up the engine and a whole lot more. So that basically is what we are looking at right now. And then we're not going to dwell long on that because we're going to have to do a whole lot more. But let's first of all look at the quantity of heat. Quantity of heat is a measure of three things: mass, specific heat capacity, and temperature change. So if you want to know how much heat a body has, we look at the mass of the body, we look at its specific heat capacity, and we look at the temperature change the body has undergone. That will decide the quantity of heat the body has. Let's give an instance of that. Imagine that I take a piece of yam from a cooking pot. Okay, I take a piece of yam from a cooking pot and I cut it up, maybe one small portion and a large portion. Now, you would agree with me that it wouldn't be too much of a problem eating the small portion. If you throw the small portion into your mouth, yeah, you are going to get a level of discomfort because it's quite hot. So it will emit a measure of heat. But then if you put the entire larger portion, even though the temperature of the pieces are the same, because it's from one piece you broke it into two. So temperature is the same for both of them. But one of them is quite big, the other is quite small. If you put the bigger portion into your mouth and try to eat it, you are going to get a whole lot of discomfort. It could even lead to burning of your tongue. So where am I going with all that? We say that quantity of heat possessed by a body is heavily dependent on mass too. The bigger piece of yam has a bigger mass than the smaller piece of yam. So because the mass is bigger, it will have more quantity of heat, even though the temperature of the two of them is the same. So we have the same temperature, but one of them is bigger than the other, and therefore the bigger one has more energy stored. That's more heat stored in it. A good example of that again is if you try to raise the temperature of your bathing water, for instance. Now let's imagine that you have a bathtub half filled with water, cold water, and you don't want to bathe with cold water. If you turn just a cup of hot water into that bathtub, it will heat up the bathtub. It will heat up the water in the bathtub to a certain degree. It will get reasonably hot. But if you take water of the same temperature, but bigger, let's imagine now you now take a bucket full of water of the same temperature as that cup of water and turn it into the bathtub with the same quantity of water in it. You would agree that this time around, the temperature of water in the bathtub will be higher than when it was just a cup of water, of hot water that was turned into it. So it tells you that even though two bodies may have the same temperature, but one of them has more energy stored in it because it has greater mass. So that basically talks about the mass and how mass affects the quantity of heat a body has. Now let's speak about specific heat capacity. Now, specific heat capacity has to do with, we say the quantity of heat that is capable to raise the temperature of unit mass of a body by 1 degree Celsius or 1 Kelvin. So if I look at it from the formula, it goes Q equals M delta theta. Remember, M is the mass, Q is quantity of heat, delta theta is the difference in temperature or temperature change. Now, once again, specific heat capacity is the quantity of heat required to raise the temperature of a unit mass. Unit mass could be 1 kilogram or 1 gram of a substance by 1 degree Celsius or 1 Kelvin. So that said, if a body is assigned 400, by the way, heat is measured in joules. Heat is measured in joules. So if I want to get specific capacity formula, unit, I'll have joules per kilogram, because you're having mass divided by it, and by Kelvin. So this is the unit for specific capacity. I just gave it 400 joules kilogram per kilogram per Kelvin as specific capacity. That is for a substance. What substance? Copper, for instance. Copper has this heat capacity, specific capacity. Water has a specific capacity that is even much higher. It is 4,200 joules per kilogram per Kelvin. What does this mean? It means that if I take 1 kilogram of water and I take 1 kilogram of copper and I subject them to the same amount of heat. Okay, by the time I've passed 400 joules of heat into copper, its temperature would have risen by 1 degree Celsius. So let's picture that both of them used to have the same temperature of 20 degrees Celsius before the whole experiment started. Same temperature, 20 degrees Celsius. I supply enough heat. Once it is 400 joules of heat supplied to copper, temperature of copper would have risen from 20 to 21. However, temperature of water will remain 20. If I go on supplying heat, by the time I've supplied 800 joules, that's 400 joules plus 400 joules. After another 400 joules, like I've just showed, temperature of copper would have risen from 21 to 22. Meanwhile, water has not changed temperature. It remains at 20. I supply another 400 joules of heat to copper, and the temperature has risen from 22 to 23. So with 1,200 joules of heat supplied to copper, to 1 kilogram of copper, I have successfully raised the temperature by how much? By 3 degrees Celsius. Whereas all of the 1,200 joules of heat supplied to water has not even changed the temperature at all. It all comes down to specific heat capacity. The capacity of a body to absorb heat is quite different from the capacity of another body to absorb heat. Like I said with these figures, copper, it takes just 400 joules of heat to raise the temperature of 1 kilogram of copper by 1 degree Celsius or 1 Kelvin. Whereas it will take a lot more joules of energy to be able to raise the temperature of water by 1 Kelvin. I would require 4,200 joules of energy, that's of heat energy, to be able to raise the temperature of water by 1 degree Celsius. So let's come back here. It means that by the time I go on supplying heat here, and I've supplied up to 4,200 joules of heat. Now, we ask ourselves, how many 400 joules of heat would we find inside 4,200? If you divide this by 400, you will get the 2 zeros out and have 10.5. So there are 10.5 units of 400 joules. 10.5 400 joules, that will find inside 4,200 joules of heat. So it means once I've been able to supply up to 4,200 joules of heat to copper, I would have raised the temperature from 20 degrees Celsius to 30.5. That's a good 10.5 degrees Celsius increase in the heat, in the temperature of copper. And then will I have successfully raised the temperature of water just by 1. So they all started, both of them started at 20 degrees Celsius. After I've supplied 4,200 joules of heat to both of them. Copper has been raised to a significantly high temperature of 30.5 degrees. That means it gained 10.5 degrees Celsius. Water would have just gained 1 degree Celsius with the same quantity of heat. That shows you that they don't have the same heat capacity. Water, of course, has a whole lot more heat specific capacity than copper. If you want to put this into practice too, you could just boil water in kettle. Boil water in kettle for a while, and once the water has boiled, just transfer that water into a bowl, a plastic bowl. So water is in a plastic bowl, the kettle is left empty to cool. Now you would agree with me that if you leave both of them to cool, the kettle cools faster than the water in the plastic bowl. Now that you have separated them, but while they were together on the stove or whatever device you are using to cook, probably you are using a gas cooker to boil, whatever device, while they were together, they had the same temperature. But the moment you separate them out, water will slowly cool. It will take a while for water to cool to room temperature, whereas that kettle cools faster. It all comes down to what I was explaining, the specific capacity. Water tends to, because water has a very high specific capacity, it does not quickly get heated up. Neither does it quickly lose its heat. So it takes a while for water to get heated up, to have a raise in temperature, and it also takes a while for the temperature of water to drop. For copper, it is the reverse. Copper gets easily heated up. 400 joules of heat added to 1 kilogram of copper will raise temperature by 1 degree Celsius. But then, at the same time, it also cools down faster. So if the kettle was made of copper, it will cool quickly. If it was made of iron, it will cool also quickly, but probably not as quickly as copper. But then, of course, it will be even faster than that of water, because water has a very high specific capacity. So the specific capacity of a body is also another thing that determines the quantity of the heat. For a body that has high specific capacity like water, if you have a certain quantity of that water, you are going to discover that for the same mass of of another substance, water tends to have more quantity of heat, because even though they have the same mass, water has higher specific capacity, and as such, it will have more heat stored. So let's put it in perspective. If I take 1 kilogram of copper and take 1 kilogram of water, all right, and they are the same temperature, there are three, don't forget, there are three major properties that influence heat. So now I'm assuming that they have the same mass and they have the same temperature. So what is it that is different between them? Copper and water don't have the same specific capacity. If you now decide to use these two substances to cool a body, let me imagine that I'm cooling a body with copper at 20 degrees Celsius. Let me raise it to say 80 degrees Celsius. And I want to cool another body of the same type with water at 80 degrees Celsius. At the end of the day, no, rather, I'm talking of raising the temperature, not even cooling. Let's raise the temperature, for instance, now. If I use 1 kilogram of copper at 80 degrees Celsius to try to heat up a body, and I use 1 kilogram of water at the same temperature to heat a similar body, the one I'm using water to heat up will eventually get more heat. It gets more heated up and have a higher temperature raise than the one I'm using copper to heat up. Why? Because water has a higher specific heat capacity, and so it stores more energy. So these are the three factors. And of course, the higher the temperature of a body, the greater the energy stored, the greater the temperature, the heat energy it has. So 3 factors that influence heat. So you can see why heat, energy, and temperature are quite different. Temperature is only a property of heat, but heat is what? Involving 3 factors here: mass, specific capacity, and then the temperature change itself. So one should not misconstrue the two of them. To wrap up this session, we say, once again, heat is a form of energy and it is measured by calorimeter. It is dependent on the mass, specific capacity of the body, and then temperature change. Whereas temperature is just about the degree of hotness or coldness of a body. So in the next slide, we are going to have some calculations involving heat. All right, so based on what we've discussed so far, Let us consider the following questions as our assignment. The first one reads thus. Mention 4 home appliances that deal with heat conversion. So, go ahead, mention any 4 appliances that you know has to do with heat conversion. 2, write the energy conversions that occur in the appliances above. Now, your answer might sound like this. Let me just give you another appliance that doesn't have anything to do with heat, for instance. Let's take a TV, for instance. TV, home appliance that has to do with electricity conversion, converting electricity, for instance, to light and sound. Of course, this will not be a valid answer in this context because this doesn't have anything to do with heat. But I'm just giving you, for instance, how you would write an answer, how you would answer number 2. You specify the appliance, and then, of course, you would have specified the appliance in the first question. In the second question, you are only telling us the energy conversion taking place. For instance, for TV, it is electricity being converted to light and sound. So that will be all in this session.